guys, hope you're all doing well. Okay, so in the last session, we talked about your physical quantities. We talked about the two divisions we have inside physical quantities, being the base quantities and derived quantities. We talked about SI units. So I'm going to show you guys the table that we have for the SI units, right? Where we have different units and we have different quantities and different units and different symbols for that, right? So we have length, time, mass, temperature, current, uh, light intensity, amount of substance, and so on and so forth. All right. So I want you guys to take a screenshot of this, go through it, and yeah. We talked about a numerical magnitude in the previous class as well, right? A numerical magnitude, let's suppose 5, right? So let's suppose we have the number 5. So why is it so important for us to include a unit next to a magnitude? Why is it important for us to describe a quantity within magnitude and a unit? Because if a quantity is not described with an appropriate unit, it would not make sense. Okay, let me repeat that for you. Let's suppose we have just the numerical magnitude here, the number 5. All right, it does not have a unit here. Okay, it would not make sense. So it's very important for us to write down an appropriate unit next to the magnitude, okay, so that it makes sense of something. All right, so the number 5 on its own means nothing, right? It means nothing. Similarly, if I was to write 5 seconds, if I was to write 5 meters, then you would know that, okay, I'm talking about the time here. I'm talking about the length here. Alright, so it's very important for us to describe a quantity with the appropriate unit so that it makes sense. Okay, because whenever you add a unit next to a magnitude, it starts making sense, because obviously we've went through the chart, we know what seconds is for, we know what we use kgs, kilograms for, we know what we use ampere for and stuff like that, right? So that's why. Okay, so that was it. I mean, we've already talked about SE units before. We know why we have SE units. It's basically a baseline for everyone throughout the world, so that everyone's on the same page. All right. Now we're going to talk about scalars and vectors. I'm sure you've heard of this before as well. So we have scalar quantities, and we have yeah. So we have two further divisions inside the physical quantities. We have scalar quantities, we have vector quantities. All right. So what exactly do they mean? All right. So scalar quantities are basically those quantities which do not have a direction. They only consist of a magnitude, meaning how big or how small is the only thing that we can make out of it. Right. For example, let's suppose we have mass, we have length, we have time. Right. So let's see. For mass, we can say that, okay, this thing has a mass of, let's suppose, 50 kilograms. This thing has a mass of 105 kilograms. Alright, so it only has the magnitude with it. Alright, similarly, when we talk about time, the volume, it would have, let's suppose, this is 5 centimeter cube. This is, let's suppose, we have another thing which is 10 centimeter cube. Right. Similarly, when we talk about speed would be, let's say this thing is moving at a speed of 10 meters per second. All right. So we're only concerned with the magnitude over here. We're only concerned with the magnitude here. We don't care where it's headed. We don't care what the direction is. All right. So scalar quantities are those quantities which only consist of, they only have the magnitude in them. All right. Similarly, when we talk about vector quantities are, however, a little bit different. They have the magnitude, okay, yes, but they also include the direction of where that object is headed. So vector quantity is a quantity which has the magnitude and it also has the direction. All right, a very good example of this would be weight. Right? So we know where the weight always acts downwards, right? It acts towards the center of the earth, right? So let's suppose if I'm saying that this is 100 newtons, right? And obviously, if I say that the weight is 100 newtons, you'd automatically be able to tell that, okay, it means that a certain mass is acting downwards, all right? The force is acting downwards. Okay, so what would you say? That this has a magnitude. What is the magnitude here? 100 would be the magnitude. And this thing here is the direction, all right? There you go. I'm sorry, time would not be included in the vector thinking. All right. Similarly, we have velocity, we have displacement, we have moments, we have forces, which I've just talked about. These are all vector quantities. Why? Because they contain a magnitude and as well as a direction. All right. One more thing about vectors that we need to keep in mind: we always use an arrow to represent a vector. All right, so representation of vectors, an arrow. We always use an arrow to represent a vector. Why do we do that? Let's talk about it. So let's suppose this is, let's see, this is an arrow. All right. Now, what are two things that the vector is made up of? The vector has, number one, the magnitude, which is how big or small the vector is. And number two, it has the direction. All right. Now, why do we use an arrow to represent a vector? Because the arrow is basically representing both of these qualities. All right, it shows both of these qualities. So let's suppose if we talk about the arrowhead, right? The arrowhead gives you an idea about where this arrow is headed, gives you an idea about where it's going to go, right? In this scenario, it's going to go towards the positive side or the forward direction, all right? So the arrowhead will describe or will help you make sense of the direction, all right? And the size of this thing or the length of the arrow would help you decide the magnitude, which is how big or small that certain vector is, right? So if I was to draw a small example for this, let's do a small example. So let's suppose I have arrow 1, right? And I have another arrow 2. What can you deduce from this? You can say that, okay, the direction of both of these vectors or both of these arrows is same. However, if we talk about the size or the magnitude of this, you can tell that, okay, arrow 2 is greater than arrow, or we can use the greater than sign here. Arrow 2 is greater than arrow 1. You can see it, right? Just by looking at the length of the arrow, you can see that, okay, the first arrow is smaller and the second arrow is bigger. Okay, so the arrowhead will represent the direction of the vector, all right, and the length of the arrow would help you understand the magnitude of how big or small something is, right? So I'm going to draw a small chart. I'm going to show a chart to you guys here, just to, with the examples of the scalars and the vectors. All right, yeah. Now we're going to talk about the resultant vectors. Okay, there are different ways as to how we can find that out. We need to go over all of these methods. All right, we're going to start from the very basics by the addition method, and then we're going to walk us through the graphical method and the head to tail and the parallelogram method. All right, so resultant vectors. Okay, so before we talk about this, we need to know what resultant means. All right, so the resultant vector itself is a component of resultant, the word itself, right? So what does resultant means? Resultant is basically the outcome, right? Or let me write down. Resultant would be the outcome of something or a result of something. Alright, so when we're talking about resultant vectors, over here we need to keep in mind that there's a possibility that we have multiple vectors, alright, that are being applied or that are acting. Okay, so when we have a combined effect of those two vectors or three vectors, right, it's called a resultant vector. Whatever we get is a resultant of that. All right. In our course, we're only going to be studying the effect of two vectors. Right. So the combined effect of two vectors is called the resultant vector. All right. So let's suppose we have, we're going to talk about the methods to determine the resultant vector. That should clear out a few concerns you guys might have. All right. So the methods to determine the resultant vector. The first one is, number one would be the addition method. All right. So in the addition method of finding the resultant vector, we have two vectors. We just talked about that, right? So a vector, let's suppose we have vector 1 here, and let's suppose this is for 10 newtons, and we have another vector which is about, let's say, 14 newtons. All right. So once again, since they're in the same direction, since they have the same direction, they're headed in the same direction, what happens is you're simply going to add them. All right. If they have the same direction, you're simply going to add these two vectors. All right. And when you add the two vectors, which is 10 newtons and 14 newtons, you're going to have 24 newtons. All right. So your resultant vector is going to look something like this. That's going to be for 24 newtons. Fair enough? So your resultant vector, the first method is to do it by the addition method. Alright. Next up we have the subtraction method. Alright. In the subtraction method is technically the same thing as an addition vector. Only the direction of the two vectors is going to be different. Right. So in subtraction, the first thing that you need to notice is the direction. All right. So let's say if the direction is not same, or if the direction is different of the two vectors, let's suppose we have one vector as 5 newtons and we have another vector that is acting in the opposite direction, and is, let's suppose, let's say 24, not 24, let's make it 12. Suppose this is 12 newtons. Alright, so what happens is you're going to have to subtract them. Why do you subtract them? Because the direction of where these vectors are headed, these are opposite to each other. Alright, so you're going to have to subtract them. When you subtract 5 and 12, you're going to get minus 7 newtons. Right? So what does this minus 7 represent? The minus sign here represents the change in direction. Alright, so the minus sign, the negative sign here that you can see is the direction. Okay, so why do we call the minus sign as, why do we have, so let me draw the resultant vector first, and then we'll talk about this in a little detail. So this would be my resultant vector. Okay, over here we need to, before we move forward, there's one thing that I would want to talk about, that is the convention. All right, so by nature, by law, we obviously set a few conventions, we set a few laws that, okay, this thing would be positive, this thing would be negative, right? So if, let's suppose, if you're moving forward, you'd say that, okay, I'm moving in the forward direction. All right, if you're, let's suppose, moving in the backward direction, right, this is forward, you'd say that, okay, this is positive. All right, but let's suppose if you're moving backwards, then you would call it negative. All right, this is the convention that you set. This is the laws that you set for yourself. All right, that, okay, if I'm moving forward, that would mean I'm moving in the in the positive direction. All right, and if I'm moving backwards, that would be the negative direction. All right, and if you, once again, if you put it on a graph, let's see. Let's say if you put it on a graph, you'd know that, okay, if you're over here, that would be, you're moving in the forward direction, that means you're going to increase. Let's suppose this was 4 meters, and then you would probably come to 5, you'd come to 6, you'd come to 7, right? But the moment you start going back, you're going to start moving in the negative direction. All right, that would mean you now at 3 meters, you're now at 2 meters, now at 1 meters, 0, -1. Obviously, there is no -1 in distance. In displacement, yes. All right, because once again, that is a vector quantity. All right, so the -7 newtons over here represents, it shows that it is in the opposite direction. Okay, because once again, why is it in opposite direction? We were talking about this in terms of the 5 newton thing. All right, but now when we subtracted 5 newtons from 12, all right, or in reality we subtracted 12 from 5 newtons, so we got -7 newtons. So the -7 would help you in drawing the final answer as well. All right, it would tell you that, okay, if it's -7 newtons, that means it's in the opposite direction. All right, so that is the second method that we use for the to determine the resultant vector. All right.